And that's being said, I'd like to introduce you to our first speaker talking about identification of sewer damages by using really intelligent image analysis. We have with us from research and development of the Berlin Water Utilities, Daniel Sauter. And I hope he's already in the live stream. I can see you already, Daniel. I hope you can see me as well.
I'm in the line, I can see you, and I hope that everything works out fine with my presentation. Okay, I see my presentation. I tried to take over the control. That was a little bit too fast. Okay, yeah, thank you very much.
Wonderful. The stage is yours.
Okay, nice. Thank you for the kind introduction. My name is Daniel Sauter. As Katie said, I work at the Department of Research and Development of the Berliner Wasserbetriebe. And as the coordinator of the Sauter project, I'm really happy to have the opportunity today of presenting some of the outcomes of our project. And before I really start with the presentation, I want to emphasize that I'm really just a representative here today for the whole consortium, and that everything that I'm going to show in the next slides is really the result of a great team effort of all of the partners that you see in the upper part of the first slide. I hear some noise in the background, by the way, so please mute your microphones. The main goal of the Sauter project is to create an assistance system to enhance both the productivity and the quality of the today's sewer inspection process. And we had two main pillars in the project. On the one hand, we were working with images from existing 2D camera technology that is applied in sewer inspection. And for these images, we developed an AI-based automatic damage detection tool, as well as an automatic measurement tool. The other part of the project is the development of a 3D camera system that doesn't exist like that yet. It's a novel system, including the carrier vehicle and everything else. So this is like a really complex hardware development. And after that, we also want to develop an AI-based damage detection system. And we want to demonstrate that the 3D technology has benefits because of the additional 3D structural properties that are contained in the data. Obviously, we want to take advantage of the lessons learned from the 2D part, which we were working earlier in the project for the 3D part. Since I'm short in time today, I will only focus on the 2D part of the project, and I can't skip the slides anymore. Okay, thank you. And the assistance system for damage analysis for the 2D data that we developed comprises various steps. We start out with images from digital fisheye cameras, and commercially available software usually has the possibility of having the perspective on the left side, so from inside the pipe, or the perspective on the right-hand side, the unwrapped inner surface of the pipe. So you have to imagine that the pipe is cut open along the longitudinal axis of the pipe, and then it's unrolled. And this is what you get then. So the very first step of our, next slide, please. The very first step of our assistance system is what we call the re-engineering of the 2D images for improvement of the quality. So we see the same inner surface of the pipe again, like in the slide before, in the upper picture in the original version. And what you typically have are these distortions in the picture that you can easily see in the connections of the different pipe segments that are like curved here. And after the re-engineering algorithm, you can see in the lower picture that these lines are really straight. So this can be fixed, and other aspects like artifacts from the lighting system of the camera can also be compensated, and the contrast is also improved. So why do we do this? We do this in order to have the best possible image quality to start with for our AI-based damage detection tool. Next slide, please. And the damage detection tool that we use is based on a convolutional neural network. That was one slide too far. One slide back, please. And we were using the RetinaNet architecture so far in the project, and the results that I will show later on are still with this RetinaNet. We recently replaced it by the efficient dead neural network, and here we expect still some improvements. We trained our network on 90 sewer reaches, and we used, as Regina Gnier said before, bounding boxes for damage labeling. You can see those labels in the picture on the right hand side. The damages are like framed in these bounding boxes. And our detection tool can discriminate 10 different damage types according to the damage catalog of the Berliner Wasserbetriebe. Next slide, please. In this figure, we see the results of our detection tool. On the x-axis, you see the 10 different damage types, and the numbers in the upper part of the diagram give the total numbers of each damage that were contained in the investigated pipes. On the y-axis, we have the recall in gray. The recall is the percentage of the real damages that could be detected with our AI. And the red columns are the precision, and the precision is the percentage of the AI detected damages that are real damages, because there will always be false positives as well. And these are the results for all the damages that were detected by the AI. And we see that the recall is quite high. Actually, we have 80% recall on average, which means that 8 out of 10 damages were found by our AI. The problem is that the precision was quite low. It was around 20%. And this means that out of 10 damages that were found by the AI, only 2 are real damages and 8 are actually false positives. So next slide, please. There's the possibility of adjusting the sensitivity of the AI, and that will result in missing some of the real damages. So the recall goes down a little bit, but the precision goes up to 60%. And this might be a more satisfactory result when you have to work with it and you don't have so many false positives. But we think that the practical experience with working with this software will reveal what's like the optimal sensitivity of the AI that will result in the highest time saving. Next slide, please. Last but not least, we have the automatic detect damage measurement. So within the bounding boxes, another algorithm can recognize the damage boundaries, as you can see here with the yellow lines in the pictures. And then the length, width, or area, or whatever you want, can be calculated based on the pixel number. This is already realized for cracks, fractures, and pipe connections. And this tool is currently integrated in our inspection software. Next slide, please. All of the previously presented components are integrated in one user-friendly software that can be used for what we call assisted damage annotation then by a sewer inspection expert. So he does or she does the quality control of the automatically annotated damages. And we will do an operational test of this software at Berliner Wasserbetriebe starting this year. And we will process several thousand sewer reaches in order to be able to assess the software if it works well for us. And also we will obtain lots of new training data in order to improve our algorithm. I have a little demonstration video here, and I would ask the technical team to start it now. Thank you very much. This is the software that we developed in the project, and the first part of the video shows how the manual process would look like. Here, the inspector found a crack, for example, and then you would have to measure the crack manually. And obviously, you have to mark the damage as well. And also choose what kind of damage it actually is. And then eventually choose more attributes of the damage. So this is how it would be nowadays, the damage annotation. And the second part of the video will show how the future could look like. So now the AI is actually computed, and then you will see, the result. You will see the same pipe from the inside again, but now you see all the pre-detected damages in those bounding boxes. And actually all the information is already there. Of course, as I showed in the results, not all of the labels will be perfectly correct. So there has to be some quality control. As you can see there on the right-hand side in the upper part, there's also a map with a location of all the damages. And we really think that this time-demanding manual process can be improved with this algorithm, and we're really looking forward to the implementation at Berliner Wasserbetriebe in this year and hope that we can further improve it. That was the video. Back to the presentation, please. Okay, these are the references, and with this I end my presentation. Next slide, please. I thank the audience. I also thank our funding organization, the Ministry for Education and Research, and I'm looking forward to questions in the Q&A session.